Good morning. Welcome to this plenary session. My name is Vladimír Kučera, and I have the pleasure of introducing Dr. David B. Doman, who is our speaker today. Dr. Doman is a senior aerospace engineer with the Air Force Research Laboratory at Wright-Patterson Air Force Base in Dayton, Ohio. He received a PhD in aerospace engineering from Virginia Polytechnic Institute. He is the recipient of several awards, including the 2008 Silver Medal of the Royal Aeronautical Society for his work in the area of hypersonic vehicle dynamics and control. Dr. Doman, you have the floor.
All right, thank you. Microphone. Okay, well, I appreciate the opportunity to speak here to such a distinguished audience, and I thank the organizing committee for inviting me to speak on this topic. I spent some time here in Milan over at the National Museum of Science and Technology looking at some of the models and drawings of Leonardo da Vinci, and it's amazing to see what has come to pass over the years. And maybe one of the last things on the list would be to implement some of the visions that he would have had for flapping wing vehicles. You can see a few very interesting models over there if you get time to look. So that in mind, we'll go ahead and start. Today I'll cover the objectives of the work and show some motivating examples from nature, show a few examples of flapping wing aircraft that exist today. And I'll proceed with a discussion which would be particularly appropriate for this audience on control-oriented modeling. How do you model something with flapping wings, and how do you use those models to design control laws, and how do you tie controllability back to the design of the aircraft itself? So I'll discuss several different control strategies. We'll look at how to simulation test your control strategies, look at some experimental validation, and look at some of the subsystems interactions that occur between flexible flapping wings, drive motors, and the mechanisms. So our research objectives were to enable stabilized and controlled flight for tailless flapping wing aircraft. If we look across the world today, we can see a number of flapping wing aircraft that exist, and most of them have tails. We could look at the Festo Smart Bird, which has come out recently. That's an example of a flapping wing aircraft that's tail controlled. The so-called Wowee Dragonfly that you could go to a store and buy, that's also tail controlled. So we're interested in control of aircraft that manipulate just the wing beats themselves, changing the speed and the orientation of stroke planes, etc., to control their flight. And our objective was to achieve insect-like maneuverability. So by that I mean the ability to hover, move forward, backward, and maneuver in the lateral direction as well. So one thing as controls engineers that we have to keep in mind is that these things have severe size, weight, volume constraints. And so when you want to implement your control system on such a device, you have to be very careful not to make it too complex. In fact, some of the low-level controllers that we've developed so far have to make use of integer arithmetic. And so all the complicated trigonometric functions have to be computed offline, coded in integer form, and make use of hardware multiplies and divides on board small chips in order to make it viable to have something that fits within the size, weight, and complexity limit. Another objective of our work was to determine what's the minimum level of fidelity that we need in order to determine how to develop a control law for such a vehicle, and one that performs well. So we don't want coupled computational fluid dynamics or structural grids that take long times to compute. We're really interested in capturing the major effects and letting the magic of feedback control account for the uncertainties in the aerodynamic model. And finally, we want to map the vehicle design parameters back to controllability. That's also important. So let's look at a couple of examples from nature to get a sense for how things fly. This is a video of a hummingbird here. And you can see the majority of the wing motion occurs in a plane. So there's a stroke plane defined by the wing sweep here. Now, it's not to say that there's not some out-of-plane twisting. In particular, if you look at the twist of the wings, as the wing comes forward, the wing is twisted such that it has a positive angle of attack and it's producing positive lift. And as it goes backward, it also has a positive angle of attack, again, producing lift on both sides of the stroke. There's also some heave and plunge motion involved here as well. So if we go to look at insects, now an insect like the hawk moth shown here, you can very clearly see that there's passive wing rotation involved. If you look at the leading edge of the wings, they are relatively rigid, but the trailing edges are flexible. And that flexibility is the key to producing lift, because it's producing lift on both the forestroke and the aft stroke, because it's maintaining a positive angle of attack on the fore and the aft stroke. If we look at this film by Stephen Fry and Michael Dickinson from Caltech, they show a fruit fly with the motion of the wing, and you can see this lift vector, or this aerodynamic force vector, increasing and decreasing in magnitude. That's another key feature of a flapping wing vehicle, is that the aerodynamic forces are oscillating. They're not steady. So any attempt to control a vehicle like this using a steady control idea is not going to work. So you have to figure out a different way to handle this. All right, so we'll look at a couple of examples of biomimetic flapping vehicles. This vehicle was built at Wright State in Dayton, Ohio, and it's not unlike the vehicles built at TU Delft, the famous Delft Fly, which was one of the first to take flight. This vehicle makes use of a clap fling mechanism, and so and it is tail controlled. You can see a rudder and elevon here, and essentially a throttle controls the speed of a DC motor, which controls the flapping rate. This aircraft is essentially flown just like an airplane would be flown by an RC pilot, except that the propeller is replaced by flapping wings. That's really the main difference. So it might look bug-like, but it flies completely differently than a bug. Now, within the last year, a company in the United States called Aerodynamic produced the first tailless controlled flapping wing vehicle, the small hummingbird here, shown with its creator Matt Keenan. This aircraft does fly very much like a hummingbird. The control strategy here is to change the angle of attack on the forestroke and the aft stroke. So the wing will travel forward at a different angle of attack than it would on the aft stroke, and in that way you can create differential cycle average drag forces to control the aircraft. So there are several different ways of controlling aircraft. That's just one of them, and we'll talk about several of them today. I will note that this vehicle was designed largely using a trial and error approach, more of an approach reminiscent of Thomas Edison. They produced about 200 wings before they found a set that would actually work. And much of what we're doing is trying to put a more systematic and scientific approach in place, whereby we can design vehicles with different control strategies, different sizes and shapes, without having to go through such an extensive trial and error process. At the other end of the scale, we have the 60 milligram, 3 centimeter wingspan Harvard RoboFly. This aircraft is piezoelectrically powered, and we'll talk more about that shortly. This was the first aircraft to produce excess lift, and it did so on a tether. So it basically flew up a pair of wires and was not controlled in any way. Another aircraft here that we'll talk about at length is a 2-actuator version of this, wherein the wings can be independently varied. And this is one that we built at AFRL that's a mesoscale vehicle that will be undergoing air table testing for maneuverability as a precursor to free flight. All right, so I wanted to talk about passive wing rotation because it's a key feature of many biomimetic flapping wing MAVs. One notable exception is the Festo Smartbird, which makes use of some active twisting. So the twist is synchronized with the position of the wings through sensors in the DC motor. But in the interest of keeping the design simple and preventing large inertia loads from being present by having an actuator moving in the wing frame, passive wing rotation is a good way to get around those problems. So here you can see what passive wing rotation looks like, the general principle. The top picture is how the Harvard RoboFly works. It's basically a pair of two sheets of carbon fiber that sandwich a flexible material, and as dynamic pressure hits the wing, it bends, and it can't bend too far because there's interference between the two carbon fiber plates. So it works a little bit like a door that would be designed poorly such that it can only open up part way. But what that does, it gives you the ability to produce positive angle of attack on the four-stroke and the aft-stroke and provide lift. You can see here another model on a test stand that's got this passive rotation component in it. This is video from our lab. And here's a video from the two-wing piezoelectric vehicle at Ifac under strobe light, so you can see the passive rotation working there. All right, so let's look at the differences between flapping wing aircraft and conventional aircraft, like fixed or rotary wing aircraft. So a typical flight control engineer is accustomed to having continuously variable control inputs that he can apply to his vehicle. They'll produce steady forces and moments. On the flapping wing side, a conscious decision was made to flap, and therefore you have nothing but periodic forces and moments to work with. So as I said before, any attempt to control the instantaneous aerodynamic forces on these wings in order to control it is doomed to failure, because the aero forces are going to peak at a roughly mid-stroke, and they're going to be very near zero at the ends of the stroke. So at first this looks like an undesirable feature. However, before the end of the talk today, you will see how it's possible to control multiple independent degrees of freedom by controlling various parameters that govern the nature of the strokes. So for example, you can control the stroke amplitude, you can control the frequency on some designs, you can control asymmetric frequency, which we'll talk about at length. That's where you control the speed of the four-stroke differently from the aft stroke. So you speed up one half of the stroke, slow down the other half. There's wing offset or bias that we can use for pitch control in some of the designs. In other words, we're basically shifting wings forwards and backwards, the oscillation point about where they work. The upstroke and downstroke angle of attack, that's just like what was done with the AeroVironment Hummingbird. Or you could actually tilt the stroke planes. So this would be like having, almost like having two helicopter rotors that can be tilted in opposite directions. So with conventional aircraft, every independent degree of freedom requires at least one actuator. Typically you have pitch is controlled by elevator, roll by aileron, yaw, rudder, etc. On the rotary wing you have cyclic pitch on the rotor, tail rotor pitch, and collective pitch to control the vehicles. All right, so the first thing that we looked at early on was the Harvard RoboFly. This was a piezoelectrically driven aircraft, and as I said, that was uncontrolled. It used a single actuator and just demonstrated the ability to produce excess lift. So it was obvious that a single actuator it would be impossible to control multiple degrees of freedom with that single actuator, but we asked the question, what if we split that actuator down the middle so that we have independent control over the left and right wings, and we leave the passive wing rotation joints in place? So to give you some idea of how the thing works, the piezoelectric actuators are mounted to a carbon fiber substrate. So when you apply a voltage to this substrate, it induces a strain in what is in effect a cantilever beam, and it produces a relatively small tip deflection. But this folded origami-like carbon structure is the equivalent of a slider crank type of a linkage that produces a relatively large angular displacement for the wing for a relatively small tip displacement. So that's essentially how these things work. And by independently actuating the wings, we looked at different ways of controlling the wings to see what we could do in terms of controlling the motion of the body of the aircraft. So this was our starting point. And I'll talk today about one control strategy that we call split cycle constant period frequency modulation with wing bias. And you'll see how you could control 5 independent degrees of freedom using 2 physical actuators. So that's not to say that there's not more inputs to the system. There are about 6 inputs to the system, but there's only 2 physical actuators in place that interpret the commands. So we have a tethered piezo-based prototype shown here that was built up at Ifac of this original concept. And then we have a mesoscale brushless DC motor-powered vehicle that we built at AFRL for air table testing. All right, so next I'm going to talk about control-oriented modeling. I mentioned earlier that aerodynamicists are very interested in these problems because there are a lot of unsteady aerodynamic phenomena at play. There's leading-edge vortex effects, there are weight capture effects, and many others. And so the question is, how many of these effects, if any, do you need to model in order to develop a model that would be good to design a control law for? And so we start with one of the simplest forms of modeling, and that's called blade element modeling. And if we look at how blade element modeling works, you basically divide the wing up into an infinite number of strips. So we do everything continuously here with calculus rather than doing discrete approximations. But the most basic oscillatory form that you can look at for a rigid flat plate that's flapping would be a cosine wave. So at the foremost position, the cosine would be indicative of 1, and at the aftmost position it would be -1. So that's what we're talking about. This is the angle, phi is the angle that the wing makes in the stroke plane. Now, blade elements that are near the root experience lower dynamic pressure than those at the tip, because the tip velocities are higher. This is a rotation type of a motion. And so you can look at the differential lift and drag across these blade elements, integrate them, and the lift and the drag forces become proportional to the area moment of inertia of the wing about the axis of rotation. And in terms of the motion parameter, they're proportional to the square of the angular velocity in the stroke plane. And finally, at the bottom, we have these lift and drag coefficients, which are empirically determined from mineral oil tank tests at Caltech. So these have been found to reproduce the aerodynamic lift coefficients rather well for low Reynolds number flows. So when they did the test, they did it with big plexiglass plates in a mineral oil tank, which aerodynamically scale to something that's that would be small, that's moving in air. If you were a flight control student, you would expect a flight control model that had steady forces and moments acting on it. But when you're looking at flapping wing vehicles, the flight mechanics become quite a bit different, because you have to consider the forces and moments produced by the left wing and the right wing separately from each other. There are sign differences between the two. And they also can behave differently on the upstroke and the downstroke. So we have here what it constitutes an instantaneous representation of the blade element model that shows you what the X, Y, and Z forces are in the body frame. So in flight control, we like to translate all these forces right back to a body frame and design controllers from there. One thing that you would notice here is that there are coordinate transformations involved. There's a sine of phi of t, but phi of t itself is a cosine wave, as we stated earlier. Its most basic form is a cosine wave. So now you have things that look like sine of cosine of omega t, and later on when we do some integration to cycle average these forces and moments, it gives rise to some interesting functions that you don't normally encounter in flight control. The moments, the instantaneous moments, which are going to be periodic, are just cross products of position vector with force vector. And we also include the effects of the rigid body translational and rotational motion to the flapping wing motion. So not only are the wings flapping, but if the wings are moving forward with the body, you're picking up velocity components from there as well. Let me talk about split cycle constant period frequency modulation. This plot shows a plot of the angle that the wing makes in the stroke plane as a function of time over one wing beat period. So the cosine wave is represented by this temporally symmetric blue curve. And if you were to look at what the lift looked like over the course of one stroke, because of the passive wing rotation, you'd see that you get two bursts of lift that will occur at mid-stroke. So your max lift's going to occur at mid-stroke on the forestroke and the aft stroke. The direction of the lift is always positive, so you'll get a psycho-average positive lift out of it. If you were to look at what happens with the drag, what happens to the drag? Well, the drag would be the same in the forestroke as the aft stroke, but it would be in opposite directions, and that means that the psycho-average drag would be zero. So the aircraft motion would exhibit a limit cycle. So the aircraft would pop up twice per wing beat because of the lift, and the drag, it would move forwards and backwards, or it could lurch forward and stop, lurch forward and stop, those types of behaviors. Now, with just two physical actuators, we ask the question, what would happen if we slowed down one stroke relative to the other one? Well, you still get positive psycho-average lift. That doesn't change. But what does change is that the psycho-average drag becomes different, because the drag directions are the same on the forestroke and aft stroke, but the magnitudes are different, because the dynamic pressure is different on the forestroke relative to the aft stroke. So the temporal asymmetry in the wing beat profile can produce non-zero psycho-average forces and moments. So if we look down here at 4 degrees of freedom that could be controlled with two physical actuators, if you increase the flapping frequency, which we call the symmetric flapping frequency, on one wing relative to another, you'll get more lift on one side than the other, and it'll cause the vehicle to tilt. If we look at the horizontal case, if you flap the wings hard on one stroke and slowly on the other stroke, you will advance further backwards than you will forwards. And so this would be like getting in a swimming pool and doing a hard backstroke and then doing a light forestroke without taking your hands out of the water. It's that type of motion. The roll can be done just the same way, hard forestroke, light aft stroke, but do it differentially left to right. And then for vertical force, you can just increase the flapping frequency to go up and decrease it to go down. So another thing that you can do with these piezoelectrics is that you can induce a DC voltage on them and cause them to take a set or a steady state bend. And when you do that, you can shift the oscillation point of the wings forwards or backwards. And so what you've in effect done is changed the psycho-average location of the center of pressure based upon the sectors over which these wings flap. And so by introducing this bias, so now the form of the waveform that drives the wings looks like an amplitude times the cosine of omega minus delta. Delta is the split cycle parameter that slows it down. And eta is the bias that changes the psycho-average center of pressure location. And with a little bit of care, you can construct waveforms that are at least position-wise continuous so that you could actually implement such a thing. So now the next step. We've talked about the instantaneous aerodynamic models, but remember that we can't control the instantaneous forces and moments. So we look at cycle averaging. So because there is quite a bit of difference in frequency between the rigid body modes of the aircraft and the flapping frequency, we do the psycho-averaging. So now you look at the psycho-average generalized forces, which are obtained by integrating a psycho-averaged or a instantaneous aerodynamic force or moment over a wing beat and dividing it by the period. And because the upstrokes can behave differently from the downstrokes, you have to carry out the integration separately. But in the end, you can calculate these integrals, and we can do it analytically, and I'll show one example of how to do it. And you can analytically calculate the sensitivities of the psycho-average forces and moments with respect to the control input parameters you have available. So here we have the symmetric frequency that you can change and the split cycle parameter as examples. So I mentioned earlier in the instantaneous model that we have a lot of interesting functions popping up that have sine of the cosine of omega t or the cosine of the cosine of omega t. And it turns out that these give rise to Bessel functions and Struve functions. The Struve functions turn out to be zero, but the Bessel functions are non-zero. As you're carrying out these integrations, you'll encounter these unusual functions in flight control. So if we just look at one of the integrals, the psycho-averaged rolling moment produced by the right wing written in the body frame, there's the upstroke integral, the downstroke integral, the expansion of it. But in the end, the form of it's rather compact. And what is nice about it is that the vehicle design parameters appear in it. So this YCP is the center of pressure location of the wing, written in the wing plane. This W is the width of the aircraft, and your control parameters appear here as well. So now you have some equations that you can work with to see how you might change the design of the vehicle to make it more amenable to control. So it allows you to look at control early in the design process. I don't know, many people in here probably suffered from people designing systems first without ever asking a controls engineer, and then coming back later and asking you to control it, and you've got problems. So it allows us to look at control early on. To calculate the sensitivities is pretty straightforward. It's just the computation of the derivatives, and the end result gets even simpler if you look at a linearized condition about hover. So if we get to the end, each one of those psycho-averaged control derivatives forms an element in your B matrix. So if you're accustomed to linear control, you like to know what's in your B matrix, and at least you want to get the sign right, because if you don't have the sign right, the feedback loop will have the wrong sign. You could be destabilized. So this B matrix here effectively tells you what the changes in the psycho-average forces and moments are relative to changes in the symmetric frequency, the split cycle parameter, and the wing bias associated with the left and right wings. And one thing that we can see from this matrix, it turns out by inspection you can determine that it's rank 5. One good thing about the matrix is that it's relatively sparse, but not too sparse, which means that there's a lot of input decoupling here. This control strategy yields a lot of input decoupling, and so that means that the control law doesn't need to be as complex as it might have to be for something that chose a different control strategy. Everything here is written in terms of the right wing because there's some symmetries and asymmetries due to left and right. But again, the Bessel functions and the design parameters show up in each individual element here. There are 36 elements, but you need to calculate 108 integrals in order to get your 36 elements. So it's a rather involved process, but we believe worth it in the end. The one row of all zeros means that you can't control the psycho-average side force on the aircraft. So that's one thing that you couldn't do. But it really doesn't matter, because if you want to maneuver in the lateral plane, you can always roll and translate or bank and translate. So you can have a higher level control loop taking care of that. So once you have such a model, we'll look at how you might implement a controller for something like this. And the easiest thing to look at is a very simple 1 degree of freedom altitude tracking problem here. and looking at what the physics are. This is basically the Harvard RoboFly on the pair of wires that moved vertically on, and this is modeled by a point mass with just gravity acting on it, and a time-varying lift force. So this lift force has the form of sine squared omega t. Sine squared omega t has two positive peaks in it, indicating the two bursts of lift that you get at mid-stroke. If you look at the analytic solution to the differential equation, you can see that the aircraft will stay in the vicinity of its starting point if certain conditions are met. One of them is that the initial velocity is 0, and the other one is that the psycho-average lift is equal to the weight. This term circled here is a statement that psycho-average lift equals weight. The one thing that all the cycle averaging doesn't tell you anything about it is what do the limit cycles look like. And the limit cycles in terms of position look like have the form of cosine of 2 omega t. Again, you get two positive bursts of lift that cause that. So let's look at what you would do if you wanted to control the altitude of this aircraft on these wires. If we had the ability to measure the altitude rate and the altitude, we could, in concept, produce a control law that turns this double integrator plant into a damped harmonic oscillator. And that's only if we could produce a steady force. But we can't produce a steady force, as we said before. But there is a mapping between the steady or the psycho-average forces and the form of the waveform that's oscillating the wings. And that's what this block diagram showing here is basically inverting the relationship between psycho-average force and frequency. Again, there's a quadratic relationship between this psycho-average force and the frequency of the wing, and that's that produces a oscillator frequency command. Now, there's a cycle zero order hold in place, and as opposed to a conventional zero order hold that works on a fixed clock, we look at where the wing beat is in the stroke plane, and we only update the frequency to the oscillator once each wing beat. And in the end, you produce a frequency command to the oscillator that drives the wings, that produces an instantaneous force, but it has a psycho-average force that satisfies one of your necessary conditions for hover. Skipped one. All right. The 6 degree of freedom motion controller works just like the 1 degree of freedom motion controller, only this is done multiple times. We have damped harmonic oscillator loops set up, and there's a bit of control mixing going on. So that B matrix that we started with, we have to do a pseudo-inverse of that B matrix to compute the required control inputs to the vehicle. And there's two cycle averaged, or there are two cycle zero order holds, one for the left wing and one for the right wing. And three inputs to each wing. Again, two physical actuators, but 3 inputs that describe the type of motion you want those actuators to produce. So this is a simulation of a flapping wing vehicle. If you listen closely, you can hear something that's buzzing. That's the waveform that's being applied to the actuator, piped through the MATLAB sound generator. And there's really no modifications made to that. It was interesting to hear it because it does sound a bit like a bug. There's kind of a warbling sound and a buzz going on. But in this case, the psycho-average control model is being applied to a model of the vehicle that's being influenced by the instantaneous forces of moments. All right, so we're not really testing the controller on the same thing that we designed it for. It includes the periodic effects of the forces of moments. So this is basically the first step in validating that such a controller would work. Incidentally, that simulation also included some unsteady aerodynamic effects. We have what we call phase index table lookups that account for differences in the lift and drag coefficients throughout the stroke. So some of the unsteady aero is included in that as well. We have now generated a general control framework for control-oriented modeling in that we haven't just looked at the split cycle, the symmetric frequency, and the bias, but we've also looked at the effects of changing stroke amplitude, upstroke and downstroke angle of attack, and stroke plane inclination. And many different implementations of flapping wing vehicles have been proposed. Here's another variant of the RoboFly where the line of centers of the linkage is changed. And the effects of these actuators can cause different types of behavior in changes in the amplitude, bias, angle of attack, etc. And you might not have direct control over these parameters. Some mechanism may be in place to take care of it. So we have gone through and calculated psycho-averaged control derivatives for amplitude, frequency, split cycle, etc. And a lot of work went into that. So many integrals were calculated and many derivatives were calculated analytically. But if you go to a new design that hasn't been conceived before, there are geometric relationships which tell you how the amplitude might change with respect to some servo control input, or how the frequency might change, or the split cycle parameter could change. And those are design dependent. They can be computed as a secondary process. Usually they're just geometric relationships, and you can get them. But by taking by using a multivariable chain rule, you can compute the change in the psycho-average force of moment relative to any type of control input you might have at your disposal. Another thing that came out of the work so far is what should the designer of a flapping wing vehicle be looking for in terms of controllability? This goes back to the problem of thinking about controls last. We need to think about that early in the process. And so some very simple necessary conditions fall out of the work. It basically says that the psycho-average lift has to be equal to the weight, and all the other psycho-averaged forces and moments have to be equal to 0 in order to stay near the equilibrium point. So what you can do when you're designing a vehicle is to try to enforce as many of these things as possible for your neutral control condition. This is like trimming an aircraft. You can select your flapping frequency and the amplitude of the flapping based on the vehicle weight. Another thing that you can do is to place the wing root hinges in line with the center of gravity. That way, when the aircraft powers up, it doesn't have an immediate tendency to tilt or pitch forward and move away from equilibrium. And the nominal control positions have to be offset in order to compensate for any upstroke or downstroke velocity asymmetry. We talked mostly today about the piezoelectric powered aircraft, but when you have DC motors driving 4-bar linkages or nonlinear linkages, you can get different velocities on the four-stroke versus the aft-stroke if you run the motors at constant speed. So in those cases, you need to compensate for the velocity asymmetry for trim using other mechanisms. All right, so these are some results that were produced at Wright-Patterson Air Force Base at the Air Force Institute of Technology. These show the piezoelectric actuator driving a wing, and if you look at this closely, you can see that the wing is going faster on one stroke than the other. This is a strobe type of a video. Now in order to make this happen, it was not a trivial process. One of the things that cropped up was that we found that when we drove a piezoelectric actuator in a wing with a split cycle waveform, we could only reproduce the split cycle motion up to about 1/5 of the first bending mode, or the first natural frequency of this combined mechanical piezo system. What happens is the split cycle signal has multiple Fourier components, and the higher order modes will get amplified by the resonant peaks in the piezoelectric actuator's frequency response. So what was done here was to look at the frequency response of the actuator and produce an input that, when applied to the actuator, produced a split cycle motion. So this is done by inverting the magnitude at two discrete frequencies. So we keep two Fourier components of the split cycle cosine wave and invert the magnitude of the frequency response and adjust the phase to compensate for phase differences between the transfer function of the actuator at those two discrete frequencies. And you can do what's called discrete harmonic plant compensation. So if we look down here, you can see these waveforms being applied to the actuator. Right here is an input, and it looks nothing like a split cycle signal. However, the output of the plant, when this signal is applied to it, looks like a split cycle signal. All right, so it's not really a pole zero cancellation per se. You're shaping the input in such a way that you produce the desired motion in the output. These are the first tests of some of the control strategies that we talked about today. This is the top one here is going to show wing bias. This thing's tethered and constrained to rotate only about that pivot point. But here in a second, you'll see the wings shift backwards. Okay, here you can see the cycle average CP moving backwards. Here it's moving forwards and it straightens up. Down here we're doing amplitude modulation, differential amplitude modulation on the wings, left to right, and you can produce this yawing motion in that fashion. So other tests were done on this vehicle on a force balance. The trends that we expected from the cycle average analysis did show up. The amplitude of some of the forces were near the noise floor of the sensor that we had. It's one problem that just about everybody has with these small flapping wing vehicles, is that the forces are so small that we just don't have force balances that are adequate to measure it. You see a lot of statistical variation in the results, but the trend lines, the slopes that we expected are there. A couple things that we didn't expect are also there, like side forces being produced by span-wise flow over the wings. We also have an Airtable experiment that we're working on. This shows some of the work here, and we've developed some new methods for producing carbon fiber wing structures that use silicone molds. We do our development of the motor controllers, in this case, the brushless DC motor controllers on these development boards, and reduce them down to surface mount configurations that we can put on a puck and slide on an Airtable to get around some of these force balance issues. We want to really just test what's the quasi-steady motion of the vehicle under the influence of these flapping wings with changes in split cycle and frequency. And one of the other details here, this goes back to the issue of having 4-bar linkages and motors driving them. If you were to look at this 4-bar linkage to drive a rocker arm to flap the wing, and you applied a constant voltage to a brushed motor or a constant pulse width modulation signal to a brushless DC motor, you would find that you would produce an asymmetric velocity profile. So velocity is a little bit lower here than it is here. And so in order to trim this vehicle up, the brushless DC motor has to be driven in such a way as to invert the kinematics of the linkage. So if we look at the pulse train driving the brushless DC motor, you can see it's stretched and compressed here. And that is done to invert the linkage kinematics so that we can produce the right root rocker motion. So we look here at a strobe picture of this DC motor configuration on the stand, one of the things that will strike you is how much wing deformation there is. There's quite a bit of twist in the wings. There's also quite a bit of structural deformation. And so while the aerodynamicists have long been intrigued by the unsteady aerodynamic phenomena at play, there's also significant structural phenomena at play. You're actually getting what it amounts to larger amplitudes and more speeds at the ends of the stroke than you would have predicted using the blade element models. And so these are things that your control laws are going to have to be robust to, the effects of the structural dynamics, particularly on these flight weight vehicles. If we look at this high-speed video here of another one of these wings, you can see the passive rotation, and you can see some out-of-plane motion as well. So all these things come together to produce a problem for controls engineers. They need to make robust control laws, but they have to be simple enough to implement on these small vehicles. So we did take some time to look at the interactions that take place between the flexible flapping wings and the drive mechanism. These primarily become issues at the mesoscale, what I call the mesoscale, where you have the brushless DC motors rather than the piezoelectrics driving things. It turns out that there are pretty significant interactions between the drive motor, a flight weight drive motor, the gear train, 4-bar linkage, and this flexible spar. We took the time to derive a system of nonlinear ordinary differential equations for this system using a Lagrangian technique. Part of the reason was we wanted to offer a tool for designers to match the motor to the loads that would be encountered. That's not a trivial problem either. Here shows one of the interesting things we observed. This is a high-speed video, 2,000 frames per second, of a DC motor linkage driving a spar, just the spar, no wing. And what's striking about it is that at about mid-stroke, that spar appears to stop, or come very near stopping. So that's really what prompted the study on the interactions. What's actually happening there is there's the first bending mode of the spar is excited, and at the end of a stroke, you're getting this maximum deflection and strain energies building up. The rocker arm's pulling it forward, and then at some point, the motion of the spar is starting to reverse because there's a difference between the frequency of the drive and the natural frequency of the spar. So the spar is going backwards at the same speed that the rocker's going forward, and the net motion is practically zero. Well, this is kind of important because dynamic pressure governs what the aerodynamic forces and moments are going to be on the vehicle. And if this sort of behavior exists, it's something you want to know about. So this shows a simulation here of the same phenomena. One thing that I'll call your attention to is near the stroke reversal on the audience's right, you'll see that green gear slow down. So that is a result of the limited torque of the motor. So the motor really doesn't have enough power to drive the spar at a constant speed. And so not only do you have strain energy interactions here, but the torque limits of the motor cause the motor speed to vary as a function of time. So applying a constant voltage to a motor does not imply that you'll get constant speed out of it under loads like this. And we did some painstaking work to match all the physical parameters to get representations of those in the simulation. We got a validation of that model. So this is the crank frequency up here. It's varying as a function of time. You can see the encoder outputs, and you can see what the spar deflection looks like as a function of time compared to our camera measurements, some spot camera measurements here in the red and the blue. If you slow everything down and you look at what the spars look like as a function of time, that's rather enlightening as well, because what you see are some dwell points, lots of spars stacking up on each other in different positions. And if you compare that with just the kinematic representation, Now, there's quite a bit of difference. There's about 10 degrees of extra amplitude just on one side, and that means that you're getting extra speed out of the stroke toward the end. And so there's some areas where you're getting more force out of the wing than you had predicted, and there's several areas where you're getting less force than you would have predicted. So this plot shows a representation of what the aerodynamic forces look like on the wing under the pure kinematic case, which is shown in green, and in the dynamic case with the spar dynamics included. And you can see, as I said, there are places where the aero forces are lower than the kinematic case, and there are cases where they're higher. But in the end, it turned out that the kinematic aero forces are about 24% lower than those experienced by the dynamic system. So the inertial loads that are in place that are causing that spar to deflect more actually buy back some force. So one of the other things that I wanted to mention was that there are examples in nature that show that insects drive their wings near resonance. Okay, and so as an insect is driving its wings at resonance, it's not wasting any energy reversing the inertial loads. It's putting all its energy really into the aerodynamic forces, and that's one of the features that we wanted to preserve with the split cycle constant period frequency modulation. The constant period piece of it came from the fact that we wanted to keep the wing operating near resonance. And with that discrete harmonic plant compensation method that we discussed a little bit earlier, you can operate the wing all the way up to resonance by using the input shaping that we discussed. So this is the sort of behavior you can expect if you're not operating at resonance. And we have not been able to find a pairing between a flight weight wing and a DC motor combination where you can operate that whole system at resonance just yet. So that's one of the things that we want to look at here in the future. We also have done some modeling that gives you what the out-of-plane bending and torsional degrees of freedom look like. So here's a simulation of that up here. Down below, we see a 3D dwell, what I call a 3D dwell plot. The green represents the chord, and the blue represents the spar. But again, you see the twist and the out-of-plane deformation here, even on the model. All right, so rather than reiterate all of the things that I've shown today, I think maybe one of the most striking things is that it looks promising that we'll be able to control 5 independent degrees of freedom with 2 physical actuators. At least from the aerodynamic point of view, that looks viable. The effects of the inertial loads on the wings is open to some discussion, and that's what we hope to find out when we conduct our Airtable tests later on this year. The force balance test with the piezos were showing the correct trends that we had expected to appear, so that does look viable. The other key is that we try to keep everything analytic so that we can make direct ties between the design of the aircraft and its controllability. And for future work, the biggest problem is probably size, weight, and power. Everything that we put on board has to be small, and it can't be very complex. And at least in the near term, until we get more sophisticated computational capability in small packages, our controllers are going to have to be implemented with some high-speed integer arithmetic operation with hardware assist. Even on these DC motor-powered vehicles that aren't flapping that fast, you're talking about making decisions on the order of microseconds about what you're going to do to apply a voltage to an actuator. The wing motions for sensor feedback are on the hockey puck version are measured by encoders. And these are not very nice devices from a feedback control point of view because they're quantized both spatially and temporally, and it complicates the controls. The vehicle motion sensors for something that's working in free flight and has a stability augmentation system in it. We're going to need very small inertial measurement units, perhaps small GPS to fly them. So we may be able to get them on a mesoscale aircraft, but getting them down to something that's going to fit on the end of your finger is quite another story. The piezoelectric powered aircraft also require power conversion. The batteries we have today are small, but they're low voltage, high current devices, and a piezo needs exactly the opposite. So you need some power conversion, lightweight power conversion on board. And we need systematic methods to design flapping wing MAVs with the controllability considerations. And in particular, we need to determine what is the minimum level of fidelity required to produce adequate controllers. And I think we're going to answer a lot of that with these airtable experiments and force balance experiments before we actually go to free flight. If you put an RC pilot in a loop, they could probably fly it. But if you want to do it autonomously, it's going to require some extra work. So with that, I'll conclude the talk. I appreciate your attention.
Thank you, Dr. Doman, for a very, very interesting lecture. In fact, it is a good example of a cybernetics approach, exploiting the mechanisms that are present in living organisms in order to build new machines. Now, I'd like to invite questions or comments from the audience.
Do I need to use the microphone, or can you hear what I say? Okay, thank you. Thank you very much for a very fascinating talk. I wanted to ask you, instead of using sine waves for the piezo, why don't you use pulse-like signals? The calculations will be much easier if you do this.
Well, that's true. We've looked not at pulses. We've looked at triangular waves to drive them. You can do similar sorts of things with a triangular wave. It does make the calculations easier.
Yes.
There's no doubt about that. And yeah, so there's nothing special about the sine wave. It just turned out to be the first thing that we had picked, and wanted to test the viability of this velocity differential, four-stroke to aft-stroke.
The other question relates to implementation. Have you thought of using analog computation instead of doing it digitally? I've seen many other MEMS applications where you use much less silicon surface if you go the analog way.
Yes, I suppose that would be possible, but we haven't considered it in this case.
There's some cool devices called FP, field programmer analog arrays, for example, and I've used them in connection with MEMS things,
okay.
With great success.
Oh, great, great. All right, thank you.
Thank you.
Some more questions, please. Comments?
All right, thank you. Appreciate it. Thank you.
Make you a question. What happens if you lose a wing?